This is our assignment on the net change theorem. Recall that if you accumulate the area under a rate curve, you will get the net change. If you want the total change, then you want to accumulate the total area above and below the axis for any positive or negative rate. So then you would do an integral of an absolute value, or you would split it up into separate integrals so that you could add the total area. All right, so in our first problem, we know that tickets are being sold for a concert. We have a function for the rate of ticket sales, and always pay close attention to your units, tickets per hour. So you need not graph these, but to make sure this is very clear, our dependent variable would be measured in tickets per hour, and our independent variable would be time, the number of hours. So you can see why when we're doing an area, we would take the x units times the y units, and our area would be the number of tickets. That's the net change theorem in a nutshell. So, without using a calculator, can we find the number of tickets sold in the first hour? We could actually graph this, by the way. This is a linear function with a slope of 134. So, 3 tickets have already been sold. So, perhaps the owners of the venue already start with 3 tickets before tickets go on sale. So, in any case, we know that the number of tickets sold in the first hour is the integral of the rate function from 0 times 0 to time 1. So we can put our function here, dt, and we know how to integrate this power rule. Raise the exponent to 2, divide by 2, and this would be a 3t, and we evaluate from 0 to 1. We like when one of the limits is 0 because it makes these variables disappear, so we just need to put 1 in here. So we would have 67 times 1 squared plus 3 times 1. And then, of course, you're not going to write the second part here, but to make it clear that we're always using the fundamental theorem to evaluate a definite integral. So we will come up with 70 tickets sold in the first hour. All right. And then we have a graphical example. So we have a velocity graph measured in centimeters per second. So our time would be measured in seconds. So again, notice your units. If you did an area, vertical times horizontal, you would come up with centimeters. So we can just start chugging away at this one using our geometry. So first from 0 to 3, we have a height of 20. So think what we're actually doing here. You don't have to write this down each time, but we're taking 20 centimeters per second times 3 seconds. So again, to make the point of cancellation of units. So here we've got a distance of 60 seconds. You could chop this up into a triangle and a rectangle next, but to remind you of our trapezoid formula, 1/2 the base of the trapezoid times the sum of the, other way around, 1/2 the height of the trapezoid, I cannot write, times the sum of the bases. And I'm having trouble with my tablet here, sorry. Rearrange. These would be bases. The bases are the parallel sides, so the fact that they happen to be vertical here is why it's easy to mix them up. But the bases of a trapezoid, remember, from your geometry are the parallel sides. So here we actually have a height that goes from 3 to 6. So the height of this trapezoid is 3. This first base is 20. And this second base goes all the way up to 50. So the area of this trapezoid, so here we have 1/2 of 70 is 35. 3 times 35 is 105 more centimeters. And our next is a rectangle that has a base of 1 and a height of 50. So this would be 50 more centimeters for that rectangle. Here's another trapezoid. So 1/2, the base of that, or the height of that trapezoid is another 1 unit. And the two parallel bases are 50 and 30, it looks like. Does that look like it's a height of 30? I guess so. So we would come up with another 40 centimeters. And then finally another rectangle with a base of 1 and a height of 30. So our total distance, let's just start adding it up here. And I think, what does it look like? 285, if my arithmetic is correct. So our total distance. All right, so you will do some problems with geometry, not always antiderivative required. Question 3, we've got a velocity function. So again, if we were graphing, make a note, your velocity function is measured here in centimeters per second. So our horizontal axis would be in seconds. And we've got a cubic function. We need not even graph this here, though. Here we're asked to use our calculator to find the net distance traveled. So even if some of it, notice our y-intercept is negative, so we're starting below the axis. So from 0 to 12.5, we're going to have some negative and some positive area here. So the fact that we're doing net distance, we simply need to accumulate that area from 0 to 12.5. No absolute value necessary. And since our function is given here on paper, we don't have to rewrite it here. We can just put integral of v of t dt. Make sure you don't put dx here. Make sure this is your independent variable. And if it's a calculator problem, so you would put v of t as your y1 function in your calculator, and then practice integrating. And I came up with 176.602, and here's a very important point as we're getting ready to take exams. That's not the exact answer, so if at all possible, try to remember whenever you're doing an approximation to not use an equal sign. All right, what if we wanted the total distance traveled? So some of this distance traveled is negative, so if we want to add up the areas, quickest trick when you have a calculator is to simply do absolute value. So you can take your previous calculation on your TI-89. Absolute value is ABS. You can find it at the top of the catalog. I think you can find it in the math menu if I remember right. But I always just type the letters ABS. So use your alpha key, and then it would be y1 of x as your integrand. And then our independent variable is x, and our lower limit 0 to our upper limit 12.5. So that's what it would look like in TI-89 notation. Do not put calculator notation on your paper. So on your homework, that's fine if you're making notes for yourself, but on your actual test paper, you're going to leave it in calculus notation, and I come up with 200.283 centimeters. So this is all you would have to write on your paper for this problem. When it's in a calculator section, show what you're going to calculate, and then you can go right to your answer. Make sure you always label your answer with correct units. All right, number 4, we're not coming up with an answer, we're just explaining here what do we know about units. So this is really why it's so important for us to remember that an integral, by definition, is an infinite sum of rectangles. So remember that P of x represents the height of each Riemann rectangle. and the dx represents that delta x that went to 0 as the base of each rectangle. So we want to always remember that definition because it explains a lot about the units. So if we were going to graph such a problem, if p of x is measured in grams per centimeter, that would be the units on our y-axis. Here, of course, it's our g of x axis. And our x units then are measured in centimeters. So that when we do the area under any such curve, we're taking the y units times the x units. So grams per centimeter times centimeters would produce an answer in grams. All right. So what does this integral represent? It represents the number of grams produced or consumed, or we would need some more information. So here we can simply say the number of grams between 0 and what was our upper limit? B? Oh, I'm reading 0. That's A. Between A and B centimeters. All right. Velocity curve. Here we're measuring in feet per minute. Feet per minute. So our y-axis is our velocity. So feet per minute on our y-axis, or here it would be our v-axis, and our time axis in this case is measured in minutes. So what does this represent? It represents the net distance between 1 and 5 minutes. And what are we doing here? This is our 1 over b minus a. So we're taking our net distance and we're dividing it by 4 minutes. So this would represent the average height. Let me actually remind you here that our average height, remember what we did for average heights, was we took our integral area and we divided by the base, which is our b minus a, the width of our interval. So if we take the area divided by the base, that gives us the average height of this curve. And since this is a velocity curve, this gives us the average height between, well, an average height. So let's actually change it to our units here is what I guess we're being asked. What is our average height measured here in our y coordinates? So this is the average. I got to be more specific. This is our average velocity in feet per minute. So it's a y coordinate. The average height is a y coordinate. Average velocity in feet per minute achieved during the interval from 1 to 5 minutes. So you can know some formulas, but if you don't understand this type of problem, then you can't apply any of those formulas. All right, so another velocity problem. Velocity this time's measured in feet per minute, and this time we're going from 1 to 5 with an absolute value. So even if some of the velocity is negative, so here's our explanation of this case here. If this is our velocity in feet per minute, so here we would be going forward and we would get some distance traveled, but then we turn around, we have negative velocity, so we would be losing some distance. And then we turn around and we're headed forward again and we would gain some distance. So if there's more area above the axis, then you would end up in the positive direction from where you started. And if there's more area below the axis, then you actually lost distance. You would be behind your starting line. So by putting absolute value here, what we're really doing is making areas 1, 2, and 3 all positive. Remember that when you do the absolute value of a curve, the absolute value graph would flip that negative curve up to be positive. So by doing the absolute value of the function, it flips the negative area up to be also a positive area. So this represents our total distance covered or traveled between, and actually I should be specific here, our total distance in feet covered between 1 and 5 minutes. So be as specific as you can when you're asked a question like that. All right, and then what happens if we take that same value? So this is from above, so this is our total distance. What if we take our total distance and divide it by the length of the time interval? So what would be 1/4 of our total distance? What are we actually finding here? We're actually, again, finding an average height. So we're finding an average height in this case. The average height would be a y-coordinate. So this would be the average height. Let's put h-av here on your notes. But the heights this time are velocities. So this would be our average velocity in feet per minute over the interval from 1 to 5 minutes. And as soon as I write that, I regret one of my words here. We can be more specific. As soon as we put absolute value around velocity, it's no longer velocity, because velocity has to have a positive or negative associated with it. Can I erase that? That was a mistake. When we do a absolute value around velocity, then let's change to the word speed. So speed, we don't care whether it's in the positive or negative direction. So that is a big change. So remember that the absolute value of velocity switched to the word speed because we no longer have our positive and negative direction associated with it. Okay, number 7, we've got a rate at which water's pouring into a tank, centimeters per minute, and we've got a very simple rate function. So here's an example where you might say this is linear, so r of t is equal to 2t, and our r of t axis is in cubic centimeters per minute. So you might say, could I just do this one geometrically? Without using a calculator, how much water is in the tank after 8 hours? So, oops, looks like I switched here from minutes to hours. So, I wonder if I meant to do that. I think I probably did not. We could, if that was intentional, of course, we could do 8 times 60 and make that 480 minutes. Let me check my notes. All right, I'll have to remember to change this in class. In my notes, this is actually in minutes. So let's stick with, that's nice, I don't have to change my graph. So correct that on your paper. So in 8 minutes, we're looking for the amount of water that has accumulated. So we know the base of this triangle is 8, and we know the height of this triangle. If we plug 8 in, we would get 16. So we could use geometry to find this area. It's all positive, so we would get 64 cubic centimeters. So the integral from 0 to 8 of r of t dt would be 64 cubic centimeters in the first of water in the first 8 minutes. And the second part of our question is how much water in the tank after 10 minutes. So same calculation, but a new upper limit in your calculator, and we should come up with 100 cubic centimeters of water in the first 10 minutes. All right. Question 8. 2 cars start from rest, stopping, at a traffic light. Car 1 travels at a velocity given by this function of 1/2 t, and the second car travels at a velocity of 1/4 t squared. So hopefully your knowledge of common functions is going to show you the point here. The first one is traveling. I'm going to make sure that looks like a slope of 1/2. So we know that v1 of t is a linear graph, and v2 is a parabola. So the point here is that the 2 cars might change positions. So one of them might get a faster start, but eventually the other car should overtake the first car. So let's find out which car is ahead after the first 2 seconds. So by the way, we know in quadrant 1 that these are both positive. So our net distance would actually be the same as our total distance. So for the distance that the first car has traveled, we would do 0 seconds to 2 seconds of its velocity, 1/2 t dt, and we do the antiderivative, raise the exponent to 2 and divide by 2. Dividing by 2 is the same as multiplying by 1/2. So we need to evaluate 1/4 t squared from 0 to 2. So we put the 2 in there, we get 1/4 of 4. So the first car is at a position of 1 foot after 2 seconds. The second car, we would integrate its velocity curve, 1/4 t squared dt, and its antiderivative, raise the exponent to 3 and divide by it, or multiply by 1/3 from 0 to 2. So we would have 1/12 of 8. 8 over 12 is 2/3 foot. So after 2 seconds, car 1 is in the lead. Car 1 is in the lead. It looks like Carl. I want car 1. Let's maybe leave a space there. Car 1. All right. So what about after 3 seconds? Well, do we need to rework each of these? You want to show your test reader what it is that you're doing, but of course we've already done our antiderivative, so we need to evaluate from 0 to 3. So 1/4 of 9, so this car would be at 9/4 foot, and that's for car 1, and the distance for car 2 after 3 seconds, we would evaluate our 1/12 t cubed from 0 to 3. So we would have 1/12 of 27. So 27 over 12 we can divide by 3 and get 9/4 feet. So what do we know? After 3 seconds, the cars are side by side, or tied if you will. And after 4 seconds, distance 1. Oops, 1/2, I'm writing dt there when it should be t. So our same antiderivative, we just keep re-evaluating. From 0 to 4, 1/4 of 16, we would be at 4 feet. And car 2, after 4 seconds, 1/12 of t cubed evaluated. Let's try that again. Evaluated from 0 to 4. 4 to the third power is 81, but we can cancel one of those 3's. So we are back to, let's try that again. What do I want to do here? 4 to the third, not 3 to the fourth. 4 to the third would be 64 over 12. So we can divide or reduce by 4 and get 16/3 feet. So now this is 4 1/3. So now we know what's going to happen. After 4 seconds, car 2 will be in the lead. And it will continue in the lead because we know its velocity continues to increase faster. All right. At which time are the cars traveling the same speed? So that question is, when is velocity 1 equal to velocity 2? So not when are they at the same position, but when are their velocities equal? So we could ask a whole bunch of different kinds of questions like this. All right, so the best way to do this is, remember not to divide by a variable. You'd lose one of your answers. So set it to 0. We can multiply through by 4 if you wish. You don't have to multiply through by 4, but that's the kind of factoring we're used to. So we would have 2 different times. At time 0, oops, let me get back where I want to be. So back on the correct page here. When do the 2 cars have the same velocity? At t equals 0 and at t equals 1. And we are measuring in seconds. So, of course, at time 0, they're both waiting at the starting line, so they haven't started yet. Okay. And I think that's our last question.